So my name is Stefano Mezza, and I'm one of the research scientists at Imotech. My main interest is natural language processing, particularly natural language understanding. And this evening I'm going to talk about my main research interests, which are dialog tags, and a little bit of applications and background. I know a lot of people are not familiar with dialog tags because they're a narrow research area still. So I'm going to start with a brief overview of the theoretical background. Alright, let's look at these two pictures to understand the difference between locutionary and illocutionary force, which is essential to understand what a dialog is. So we have two scenarios where somebody asks, can we talk? Obviously on the right is the classic scene where the person wants to talk, while on the left the parents are actually wondering if they can talk or not. Now the difference between these two scenarios is basically given by context and by what is called the illocutionary force of the sentence. Although the two sentences are identical, the message that they're trying to carry are very different. Humans are good at identifying these differences because we know that when we talk there are social conventions, there are contexts, there's all sorts of stuff that tell us the difference. But for a computer, it's very hard to understand the difference between a question, an offer, and stuff like that. This can become very annoying in a scenario where you're trying to build a dialogue system. So if you tell a dialogue system, your volume is too high, you expect the volume to go down. Now, if the system is not aware of how to understand your message, how to identify your communication message, it will go like, thanks for sharing your opinion, because you're actually giving an opinion on the volume. But what you really want from a good user experience is the system to lower its volume. It all comes down to the difference between what the user says, what someone is saying, and the message hidden between what we say when we speak. This is a dialogue act, the meaning of an utterance at the level of the illocutionary force. So once again, let's look at an example. If you say, can you pass me the salt? This sentence has three levels. A locutionary force, which is, do you have the capability of passing the salt? This is what I'm actually saying, the shallow level of the communication. An illocutionary force, which will be the dialogue act, which is the message hidden in the sentence, what I'm really trying to say, which is, I want the salt. And then we have the perlocutionary force, which is the effect perceived by the speaker, which in this case feels compelled to pass the salt. So, dialogue acts are basically a way to encode the real message behind our sentences. And it's something that is critical for a system to understand if you want to build a dialogue system that is truly intelligent and truly gives the feeling of a conversation. Now the question is, how do you annotate dialogue acts automatically? So how do you teach a computer to understand dialogue acts? To answer this, let's first look at the structure of a dialogue act. So the input here is a sentence. In this case, the user says, hello, do you like music? The first level of a dialogue act is called functional unit. This is the minimal part of a sentence with some kind of communicative message. In this case, the user is giving two messages. Hello, and do you like music? So this is the first step. Then we need to identify the dimension of the segment. In this case, the user is giving a social obligation, so it's a salutation, and he's trying to perform a task, more specifically a question. The next step is identifying the specific function, which is, as I said, a greeting and a question. And then we have the last step, which is identifying all the additional information in a sentence. For example, the fact that the user is giving a point of view, the fact that his sentiment in this question is positive, so he's asking if the system likes music. This whole structure with segments, dimension, communicative function, and all the qualifier, this builds a dialogue act. So this is what we're trying to annotate. Now how to do that? This all depends from the application. Traditionally, dialogue acts has been done in scenarios which are called domain specific. So the idea is that the system you're trying to build has a predetermined domain. For example, restaurant reservation, flight booking, something that you already know in advance. In this case, dialog acts are very simple. They're just a flight taxonomy. You're trying to understand stuff like book flight, undo booking, confirm, choose destination. So you're literally labeling the individual actions because there are not a lot of them. And in this case, the literature on this is like very, very big. There have been experiments on hidden Markov models, conditional random fields. There's something on super vector machines. The best results are obviously on long short-term memory neural networks, which are the state of the art for most text classification tasks. But the really interesting part is domain-independent dialog act tagging. So this is the scenario in which you want to annotate an actual conversation with dialog act tags before knowing the domain. So you're into the while, the user can say anything, you can say questions, make an order, whatever, and you want to annotate that with dialog act tags. In this case, the main problem is that it's very hard to build a training resource. Now, any machine learning system needs data to learn. Well, some of them don't, most of them do. And the problem is that there's not a lot of data annotated with dialog act tag because it's a very specific annotation. It's very hard for people to understand the difference, as I explained before. So there are a lot of solutions to overcome this issue. Some scientists are trying to build a resource annotated with the standard, but the standard is big, it will take a while. They started in 2013, they still have a long way to go. Other teams are annotating existing data with the standard, which is a little quicker, and there's a work presented this year at Calling in New Mexico that is doing this. And the third approach, which is the one I'm following, is there are a lot of data. There's a lot of data annotated with dialog acts from very, very old corpora, which can be converted to the ISO standard, to modern dialog acts, and used in conversational systems. So this is currently my main research, and this was a paper that I published at Calling in Santa Fe this year. This is basically a domain-independent dialog act tagger for conversational agents. What I've done is basically, I picked all dialog corpora with all sorts of different scenarios, as I said, restaurant reservations, flight traveling, all the domain-specific one. I put them together and I generalized their taxonomy to make it compliant with a domain-independent taxonomy. The system is available online, it's on GitHub, everybody can use it. It was trained using super vector machine, which is a machine learning algorithm very used for text classification. Right now, my university team is rewriting the code with long short-term memory neural networks to achieve better results in the classification. So if you want to try the system, I would recommend waiting a couple of months when the new version comes out. The feature for the classification are a combination of grammatical features, which are the classic NLP feature you use for training, so part of speech tags, dependency parsing. We use some semantic features, so word embeddings and semantic labels. And there's also context in play, so previous dialog act. We've also done some experiment with previous word embeddings. So the way the system works is, as you can see, we picked different old corpora, there's 5 of them, which are the AMI corpus, conversations, switchboard, telephone conversation, map task, which is travel planning, Verbmobile, which is restaurant reservation, and Oasis, which is customer assistance. And we mapped them all to the taxonomy of the new ISO standard, thus creating a general domain-independent taxonomy, which we then train with machine learning. Now the question is, once you have a system like this, what do you do with that? The main application for dialog acts is obviously natural language understanding. It's the most obvious choice. Because, as I said, usually natural language understanding is approached as a task-based problem. So you classify a domain, an intent, and a slot for a specific domain. But if you have a dialog system that has no domain, you don't know how to approach it. Which is why dialog acts are a very good choice for dialog system if you want to build an NLU that is truly domain independent. My project at Amazon, the Roving Mind chatbot, was implemented in 2017. This was, for those who are familiar with the Amazon architecture, this was basically an Alexa skill endorsed by Amazon, built in a year with some support from Amazon researchers and engineers. And the objective was to build a chatbot, so a software able to converse consistently on any topic, which is why we chose to use Dialoguex for the NLU model. Now, to test our system, we annotated manually Dialoguex for data from the competition. We annotated data from all the bots that Amazon provided to us and data from our bot. As you can see, all the different parts of the taxonomy, Dialoguex taxonomy, gave very good results when annotating, which means that overall it is possible to annotate Dialoguex in a conversation. Although when the full paper from Cervone and Palias from 2017 also explains that there's a problem when giving statistics and performances on dialogue annotation, which is users tend to be very robotic when they interact with a dialogue system. They will go like, turn on the lights, please talk about music. They won't be natural, which makes the annotation easier, but it's also something that is not desirable. So these results, although being very high, they're not 100% reliable as a metric of how good Dialoguex tagging is right now. Dialoguex are also very good for all sorts of different NLP tasks. I will go very briefly for those who are interested. I missed another spot. For example, sentence boundary detection, which is the NLP task of dividing text into meaningful sentences, benefits a lot from Dialoguex. You can see the state-of-the-art from Quarteroni using just anagrams and dependency tags with conditional random fields. With Dialoguex, there's a lot of improvement, especially on the Amazon data. We found over 10%. So this is an example of something where Dialoguex helped a lot. This was my thesis project in Italy. And we also have out-of-span detection, which is currently our main research focus at Innotech. So when building Ollie's NLU system, we're trying to make Ollie aware of what the user is saying. One of the hardest things is trying to understand when the user is trying to do something that the system doesn't support. In general, building a machine learning algorithm that recognizes something that doesn't exist or is not supported is always a hard task, because you cannot provide to the system examples of all the possible interactions in the word. So we found that with Dialoguex, out-of-domain detection improves drastically. This is yet another proof that Dialoguex are a good feature when trying to build a dialogue system. So let's wrap up. Dialoguex are a very important source of information from user input. It's something that is really beneficial to know. This presentation covered some NLP tasks, but really only scratched the bottom of the barrel. They're very beneficial for sentiment analysis, sarcasm detection. It's something that when annotated correctly can be extremely useful. There's a lot of work to do still. The area is expanding significantly because with the explosion of dialogue systems, a lot of people are finding that we need this sort of information. So you will find, if you're interested, that there's a lot of papers, resources released every year. So it's really something that will grow a lot in the next few months and few years. If there are any questions?
The topic of my presentation is about RNNs and LSTMs. I wanted to describe and to give a background for people so that people would know the differences and would know which network is better to use and in which cases. So first I'll tell about RNNs and why we need them. Then I'll tell about LSTMs and I'll tell what LSTMs solve comparable to RNN. And then I'll tell about GRU, which is a type of LSTM, and it's a popular type of network now, and I'll explain why. And then I'll describe two papers which came out recently this year about universal language model fine-tuning for text classification, which is a kind of transfer learning for NLP. The thing is that transfer learning for computer vision exists already for a long time, and transfer learning for NLP, it's something that doesn't exist at all. And these two guys who wrote this paper, they created this transfer learning for NLP, and I'll describe it later. And the second paper is about deep contextualized word representations. It's about substitution for word embeddings. It's like a better version of word embeddings. And it also uses LSTM as a neural network model. And the things that these two papers, they run on the datasets which already exist, and they beat the state-of-the-art results. So let me start. As already Julia said, I'm a senior algorithm developer at Peppery, and I'm also an NLP researcher at Ben-Gurion University. So, what is motivation? Ordinary neural networks don't perform well where the sequence of data is important. On such data as time series and NLP problems like text classification, sentiment analysis, and much more. To overcome that issue, RNN were invented. And RNN is an acronym for recurrent neural network. The first paper about RNN appeared in 1990, and from that time that algorithm was used. And RNN cell not only considers its present input but also an output of an RNN cell perceiving it for its present output. A recurrent neural network is a network that consists of a hidden state H and an optional state W, which operates on a variable length sequence X. At each time step t, the hidden state ht of RNN is this state. So RNN only have a hidden state, and it can have also an optional state y, which is an output of RNN. So at each time step t, the hidden state of ht of the RNN is updated by the two parameters, ht minus 1. So ht minus 1 and xt. This one xt and this is ht minus 1, and this way we calculate the hidden state ht. So it kind of the RNN context is a kind of this recurrent state, but it helps to kind of unroll the RNN network for this kind of full network to understand how it works, and you can think about a current neural network in two ways. One of these concepts about having a hidden state that feeds back itself recurrently, but I find this picture a little bit confusing, and sometimes I think about unrolling, and you can think about recurrent, you can think, and this makes the data flow of the hidden states and the input states to output. Okay, and so which problems do we have in RNN? First of all, we have this back propagation mechanism which goes through all the cells and goes through matrix W, and each time it multiplies with this matrix W. But think about the case where the values of W are too small or too big, and if you propagate through the value through the matrix W, it creates a problem in such a way that you can finish an exploding variant problem or vanishing variance. And also there's an additional problem with ordinary RNN, so that RNNs are good at a small distance, but they are bad in the context where in the context which is separated by big distance. This problem is called long-term dependencies, and for example, the sentence "I live in Italy," and there goes some analysis sentence, and then it goes some sentence "I can speak," and we need to infer which language the person can speak. And the thing is that RNN, in theory, it can solve this problem by fine-tuning the hyperparameters, but in practice it doesn't work. So we need some other solution which solves this long-term dependencies, where the word we need to infer is separated far away from the input states, which can be in the beginning of the text, or just separated by hundreds or several hundreds of steps. And therefore we need some improvement, which is LSTM. LSTM is a special kind of recurrent neural network with a specific capability of handling long-term dependencies, and it also solves vanishing and exploding variant problem. I'll explain you later how. It was introduced by Hoyt, Schrader, and Schmidhuber, who solved the problem of RNN to remember the long-term dependencies. They designed a memory cell which is using logistic and linear units with multiplicative interactions. And LSTM, basically, its structure is much more robust than RNN, where in RNN we had only one hidden state and one network layer. Where in LSTM we have already 4 gates, and one of them is in charge of what we want to write to the network, another one is what we want to keep in the network, and and another one what we want to read from the input and put into that network. And this read gate concatenates the two network layers. So this is what I previously described. LSTM cell has this one LSTM, these two states, like the cell state CT and the hidden state HT. It has these 4 gates, and it has for each state it has a different activation function, and it has a matrix W for different it can be this matrix W can be separated by several metrics, but it's more convenient just to stack these matrices on top of each other and then multiply by the concatenation of these two vectors, ht minus 1, which is from a previous step, and xt, which is the current input for, like here here is xt is an input word for the hidden state ht, and for this sequence is a sequence of words in the sentence. So where in RNN we only have this neural layer which multiplies the matrix W concatenation of two vectors. So this is an interaction of LSTM cell with another cells, and as you can see, it has, as I said, 3 sigma layers, which activates. This one is for get gate. This is 2 for input, and this is for output. So these are 4 gates, and this is the matrix. Usually we use one matrix because it's easier to calculate in such a way, and we staple a vector xt of size h on the vector h ht minus 1 with size h, and multiply by this matrix w, and this gives us this matrix with the size for h, and then we multiply each part of it, like this part is being multiplied by a hyperbolic tangent, and we receive G gate. And this part is multiplied by sigmoid, and we receive an output gate. And after getting the output from previous state, for get gate helps to take decisions what has to be removed from the previous hidden state. And it is surrounded by this sigmoid function. So and sigmoid function like squash the value between 0 and 1, and this sigma and hyperbolic tangent, what they do is basically they act like counters. For example, if we need to remember some data, they don't change the information too much, but they change information as in the way it should be changed. So this is a Python code for calculating the forget gate, and then goes an input gate, and where we decide if we want to add new stuff to the present input and output. And in this photo, we have this IT, which is input gate, and this was G gate. But here is used. I used another symbol, but basically they both come to this operation, come to this element-wise multiplication, and then they go to the C, to the output of the current cell, and to calculate the hidden state over these operations. So to calculate the present state, as I said, we use forget gate, FT, a state from the previous cell, and input gate, what we want to add, and the G gate. And in the output gate, we decide what we want to output from the cell, and we multiply the input with a hyperbolic tangent to crush the values between -1 and 1, and then multiply the output of sigmoid function so that we only output what we want. And so how LSTM addresses the vanishing and exploding gradient problem? It addresses it in such a way that we don't use our matrix W in every cell, and this way we have like a super gradient highway, which is uninterrupted and unimpededly can unimpededly update the weight matrices and coefficients which we need to update with the backpropagation. So this I thought. Okay, RNN and LSTM can have several layers in depth. So usually you don't see very deep recurrent neural network and LSTM network. It's usually 2 or 3 layers, sometimes 4, but 4 is a maximum as you want to go. So you don't have usually more than 4 layers. I need to say that almost every researcher who does his research and uses LSTM neural networks creates his own implementation of this LSTM cell, and there is one particular. There are thousands of LSTM architectures. But there is one specific LSTM architecture which got a name because it's very useful. So it's called gated recurrent units. So instead of having 4 gates like a regular LSTM, we have here 3 gates, and what it the less neural networks we have, the less data we need to train. And so when we have a small data set, we better use GRU, and if we have a data set of big size, so we better use LSTM. So, and these are two papers which I mentioned in the beginning, and as I told in the beginning, that the first paper is about to introduce the transfer learning for NLP, and the method which two researchers propose, it uses LSTM, bidirectional LSTM. So bidirectional means that we use forward LSTM and the backward LSTM. So we take into account two contexts, and it's like a state-of-the-art neural network which is used now, like bidirectional, and it outperformed the state-of-the-art methods in 6, like IMDb, Track 6, AG, DBpedia, Yelp-Full. So it outperforms with the less error rate than the previous state-of-the-art method has. So the second paper is also kind of prove this concept that LSTM is a very powerful neural networks for classification of neural networks, and authors introduce deconceptualized word representation for models, and they use basically this type of algorithm. So they have this input, and for example, they need to calculate the word embedding, like they are a new variant of word embedding for their input, and they run through LSTM forward and backward, and they receive hidden vectors, hidden states of LSTM from forward and backward LSTM, and then they do softmax of the hidden state which were before the word, and the hidden state which were before the word from another side, from backward side, and this way they take into account both contexts, both from the left and from the right. So this is how, by the way, the forward and backward look like. So we have, as you remember, in a recurrent neural network, when we unroll the network, we have this where we go to the left or to the right, and here we go from the end of the sequence to the beginning, and basically, if we are to calculate the word embedding, or how they call it, deep conceptualized word representation. So they use the context which was here in the backward and the context which was here before the word. So that's okay, and this is the results. Here are results of that they achieved. These are results which they get by trying to use the methods which other like these authors had, and they try to reproduce, and this is the gain which they received using their Elmo word embeddings. So if you have any questions.